Good morning, everyone, and welcome. I'm Dr. S.K. Singh, and I'm glad to have you here today. We'll be exploring the topic of contamination, specifically focusing on airborne molecular contamination, or AMC. Over the course of this presentation, we'll look into what AMC is, how it impacts our work, and ways to manage it effectively. I'm excited to share this information with you, so let's get started. Let's start by looking at the traditional focus in contamination control, which has primarily been on particles and microbes. These have long been the main concerns because they're visible and easier to detect and manage. However, as technology advances, we're now facing an emerging risk that's less obvious but just as critical: molecular-level contamination, or AMC. AMC refers to contamination at a microscopic or even molecular level, which can be much harder to identify but can have significant impacts. It can affect product quality, risking the integrity of the final product. It also threatens equipment integrity, potentially leading to corrosion or other damage at a very small scale. And importantly, AMC can compromise sterility assurance, which is vital for ensuring that products are safe and effective. In fact, AMC is now recognized as a critical source of contamination, especially in advanced manufacturing environments where precision and purity are paramount. Understanding and managing this risk is essential for maintaining high standards and ensuring the safety and efficacy of our products. Let's start by understanding what AMC actually is. AMC stands for airborne contaminants that exist as molecules, such as gases or vapors. Now, these molecules are incredibly tiny, roughly between 0.2 and 3 nanometers in size, which makes them much smaller than typical particles we might think of. Because of their tiny size, they can easily pass through filters like HEPA or ULPA filters, which are designed primarily to trap larger particles. A key point to remember is that these AMC molecules are not visible to the naked eye. They also aren't controlled effectively by standard particulate filtration methods, which focus on removing particles rather than gases or vapors. Moving on to the regulatory framework, there are specific standards and guidelines in place. ISO 14644-8 classifies AMC based on their chemical concentration, helping us understand and control their levels in clean environments. Semi-standards, specifically F21, categorize AMC into types such as acids, bases, organics, and dopants, which is useful for targeted control strategies. Finally, the EU GMP Annex 1, updated in 2022, emphasizes the importance of controlling chemical contamination, including AMC, through the use of Chemical Contamination Control Strategies, or CCS. All of these points highlight how critical it is to understand and manage AMC to maintain the integrity of sensitive manufacturing processes. Let's take a closer look at the different types of AMC, or airborne molecular contaminants, classified under the semi-system. First, we have molecular acids, or MA, which include substances like hydrochloric acid, HCl, and sulfur dioxide. SO2. These are acidic molecules that can impact the environment and equipment if not properly controlled. Next are molecular bases, or MB, with ammonia, NH3, being a prime example. These are basic molecules that can also cause issues in sensitive environments. Then we have molecular organics, or MC, which include volatile organic compounds, or VOCs. These are organic molecules that easily vaporize and can contaminate cleanrooms or semiconductor processes. Following that are molecular dopants, or MD, such as boron and phosphorus. These are intentionally introduced during manufacturing, but can become contaminants if they escape into the environment. A key point here is that a standardized classification system helps us maintain control and consistency across different processes and environments. It allows us to better understand and manage these contaminants. Now let's consider the main sources of AMC. External air pollution, like sulfur oxides and nitrogen oxides, can carry contaminants into the cleanroom. Personnel also contribute. Things like skin emissions and breath can release molecular contaminants. Materials used inside the cleanroom, such as plastics and adhesives, are potential sources too. Process chemicals, including solvents and acids, are common contributors. Equipment leaks can also release AMC into the environment. And it's important to remember, every material introduced into the cleanroom has the potential to generate AMC. That's why controlling and monitoring these sources is so critical for maintaining optimal conditions. Let's talk about material outgassing, which is a major source of contamination in cleanrooms. Essentially, materials like polymers, sealants, and cables can release volatile organic compounds, or VOCs, into the environment. These emissions can vary based on several factors. For example, higher temperatures tend to increase outgassing, while larger surface areas expose more material to release VOCs. The chemical composition of the material also plays a significant role. Some plastics or sealants are more prone to outgassing than others. To give you a concrete example, imagine a plastic chair in a cleanroom. Over time, it can release organic vapors, which might seem harmless but can actually cause wafer defects during semiconductor manufacturing. That's why controlling outgassing is crucial. In fact, it's one of the primary sources of airborne molecular contamination, or AMC, in cleanrooms. Managing and minimizing outgassing helps maintain the integrity of sensitive manufacturing processes and ensures the quality of the final product. Let's talk about process-generated AMC, or airborne molecular contaminants, that come from chemical reactions during manufacturing. When these reactions happen, they often produce gases. For example, during etching, hydrogen chloride or HCl is generated. When cleaning, ammonia or NH3 is released. And during solvent evaporation, volatile organic compounds or VOCs become airborne. To give a concrete example, in the photoresist process, organic compounds are released into the environment, and these can actually affect the lithography process itself. Even at incredibly low concentrations, like parts per billion, these contaminants can have a significant impact on product quality. So, understanding and controlling these process-generated gases is crucial for maintaining high standards in our manufacturing environment. Let's take a closer look at personnel as a source of airborne molecular contamination, or AMC. Human emissions contribute various compounds like CO2, NH3, and organic vapors. These come from everyday activities such as sweating, applying cosmetics, or even just breathing. For example, ammonia from operators neutralizing photoresist can lead to defects in the manufacturing process. What's important to realize is that personnel often remain a hidden source of AMC. Even though they're not always obvious, their presence and activities can significantly impact the cleanliness and quality of our environment. Recognizing this helps us better manage and control AMC in sensitive manufacturing settings. Let's take a closer look at the impact of AMC, or airborne molecular contamination. First, it can create surface contamination in the form of thin molecular films. These films might be invisible to the naked eye, but can significantly affect surfaces. Next, AMC can alter the electrical properties of materials, which is especially critical in sensitive electronic components. It can also lead to optical haze formation, reducing clarity and performance in optical systems. Additionally, AMC can cause corrosion of equipment, leading to maintenance issues and potential failures. For example, ammonia in the environment can distort the line widths in semiconductor chips, impacting device performance. Now, why is AMC so critical? One key point is that the deposition rate of AMC can sometimes surpass the rate of particle deposition, meaning these molecular films can form and accumulate faster than we might expect. In some cases, AMC can even form monolayer films on surfaces, creating a uniform coating that's difficult to detect but impactful. Interestingly, even in ultra-clean environments, like ISO Class 1 clean rooms, we can still encounter high levels of AMC. This highlights how pervasive and challenging AMC contamination can be, making it a crucial factor to control in high-precision manufacturing and cleanroom environments. Let's talk about the monitoring of AMC now. When it comes to techniques, we primarily use ion chromatography, or IC, which is very effective for detecting specific ions related to AMC. Gas chromatography mass spectrometry, or GCMS, is another powerful tool that allows us to identify and quantify complex compounds with high precision. Additionally, we have SIFT-MS, which stands for Selected Ion Flow Tube Mass Spectrometry. This technique is particularly useful because it enables real-time monitoring of AMC levels. In fact, continuous monitoring is generally preferred over periodic checks because it provides us with instant data and helps us catch issues immediately. For example, if a door opens unexpectedly, we might see a sudden spike in AMC levels on our monitor. This real-time approach is crucial because it helps us prevent product loss. By catching fluctuations as they happen, we can take quick action to maintain product integrity and ensure safety throughout the process. Let's take a closer look at some of the advanced control technologies that are essential for maintaining ultra-clean environments. First, we have AMC filters, which are specialized chemical filters designed to remove specific contaminants from the air. These are crucial when we're dealing with sensitive processes that require a high level of purity. Next, the ultrapure air systems, or UPA systems, are engineered to deliver air with extremely low contamination levels, often achieving less than 1 part per billion, which is vital for preventing product contamination. We also use UV oxidation systems, which utilize ultraviolet light to break down organic compounds and other pollutants, further enhancing air purity. For critical processes, isolators provide a barrier that isolates the process environment from potential contaminants, ensuring a highly controlled setting. Now, connecting this to the bigger picture, the control strategies outlined by the Contamination Control Strategy, or CCS, emphasize the importance of chemical filtration using activated carbon filters, optimizing air handling systems, and selecting low-outgassing materials to prevent contamination sources. We also focus on controlled process chemistry and personnel restrictions to minimize human-related contamination risks. It's important to note that relying solely on HEPA filters isn't enough for advanced pharmaceutical manufacturing. HEPA filters are excellent for particle removal, but they don't address chemical vapors or gases. That's why incorporating these advanced technologies is critical to achieving the ultra-clean environment necessary for our processes and ensuring product safety and quality. Let's look at a practical example to see how these concepts come into play. In this case study, we're dealing with a semiconductor fabrication process where a defect was identified. The key issue here was line width variation in the chips, which can seriously affect performance and yield. The root cause turned out to be airborne ammonia contamination, something that might seem minor but can have major impacts. Because of this contamination, there was a noticeable loss in yield, meaning fewer usable chips from each production run. To address this, the team installed AMC filters, which are designed to remove airborne contaminants effectively. Additionally, they implemented continuous monitoring systems to keep a constant check on air quality. This approach highlights how identifying the root cause and implementing targeted controls can significantly improve process stability and product quality. It ties back to our overall theme of proactive problem solving and the importance of real-time monitoring in maintaining high standards in semiconductor manufacturing. Let's wrap up with the conclusion. AMC, or active microbial control, is often invisible, but its impact is highly significant. Even though we can't see it, AMC plays a crucial role in maintaining cleanroom integrity and ensuring product safety. To effectively manage AMC, we need advanced monitoring techniques that can detect even the tiniest microbial presence. Chemical filtration is also essential to remove contaminants at a molecular level, safeguarding the environment. Additionally, risk-based contamination control strategies, like CCS, are vital to prioritize efforts where they matter most. Looking ahead, future cleanrooms won't just need to control particles, they'll have to manage both particles and molecules. This dual focus is key to achieving higher levels of purity and safety. Overall, Understanding and implementing these strategies will help us stay ahead in maintaining the highest standards for clean environments. For further support, please contact us. We're here to help you with any questions or additional information you might need. Don't hesitate to reach out. Your success is our priority. And with that, I want to thank you all for your time and attention today.